Okay, so let's continue with standing waves. So here we have a string, and then if we count the number of antinodes, in this case we have 1, 2, and 3, then that would be this m here, the number of antinode. And if we only have one, we call that the fundamental mode, when there's only one node, one antinode. So the fundamental node has a wavelength of twice the length, right? If this is the length here, then the fundamental node has a wavelength of 2L. So the allowed frequencies, this standing wave can only have frequencies that are multiples of this fundamental frequency that is associated with the fundamental mode. So it would have only F1, 2F1, 3F1. The fundamental frequencies can be found as the difference between two frequencies, Fm plus 1 and Fm. So that would give you the fundamental frequency. So what is the number of, what is the mode number of this standing wave? You have a standing wave here. What is the mode number? Well, we have 5 antinodes, so that gives you m equals to 5. So now you have a standing wave on a string that vibrates as shown. Suppose the tension is reduced by 1/4 and the frequency and length are kept unchanged. Which standing wave pattern is produced out of all this? And the right answer is C. And well, if you change the tension, then that reduces the velocity by half. Remember that. The length is not changing and the frequency is not changing. So therefore m must double to keep the frequency constant. So you're going to have more antinodes here because you're reducing this, right? So this number is the same. So this m here must change. So this number remains the same. So another place where you can find standing waves is electromagnetic waves, and you can have a laser cavity, and then you have two reflecting surfaces here, and then you're going to have a standing wave that is a cartoon is here, but this would be really hard to draw. A typical laser cavity has a length of 30 centimeters. This is about 1 foot, and invisible light is roughly around 600 nanometers. That's the length. So a standing light wave in a typical laser cavity has a mode number that is or of the order of 1 million. So you would have about 1 million antinodes here. So sound wave also can produce standing waves. And so to do that, you can use a narrow column of air as you did in the lab, and those can produce standing waves. So you can have this sequence, and let me show you a simulation here. So this, you can have a tube here, and this is your air, and both sides are open. And now that produces a standing wave. Here you have, this is the displacement, right? The displacement. And here you are plotting the pressure. And the pressure is always maximum here at the center. And now let's just show some higher modes. Now we have a higher mode, a second, third. Now let's go and change the configuration. Now we have one side closed and one opened. So we have a node here all the time, and this is the fundamental. So now let's go to the first one, second one, third one. This is what happens. And then if we have both ends closed right here, so we have a node here and we have a node here. This is again your fundamental. And then you can go and see the higher nodes. So that is your sound wave in a cavity, and here you have m equal 2, and then This is a time sequence. This is the first slide, this is the second one, and this is the third one. So what happens in the first is, well, you have minimum pressure here and maximum pressure in the middle, and then here the pressure is uniform and there's no displacement, and again you have maximum pressure and minimum pressure. So this is how the sequence go. And you can then have a plot of both displacement and pressure, right? And the pressure, when the pressure is minimum at the antinode and maximum at the node. And this is a tube that is closed on both sides. And then you can have three situations. You can have close and close. And then you can have open and close. Sorry, open and open and closed. And on each case, then you have a fundamental a wavelength that is given by the fundamental wavelength is 2L, and the fundamental frequency is the velocity divided by 2L, and then m times this gives you the possible frequencies, and lambda m would be 2L divided by m. And it's the same for close and open, but it changes a bit for open and close simply because now the the fundamental wavelength is L, is 4L. So you're gonna have a wavelength that is 4L that gives you your fundamental mode, and your fundamental frequency would be the speed of sound divided by 4L. All right, thank you.